We have a few more conceptual questions here related to projectile motion. For this first one, we have a projectile launched from the ground up at an angle. And we want to know, while it's flying through the air, like this, is there ever a time when the acceleration is parallel to the velocity or perpendicular? So we know that our acceleration will always be going straight down because that's the direction we're accelerating when we're in midair, because only gravity is acting on the object. So will our velocity ever be parallel to that? And the answer is going to be no, because we're never traveling straight down. We're always going to have some measure of horizontal velocity. For the second one, is the acceleration ever perpendicular? And that does occur. We need a time when our velocity is simply in the horizontal direction, and that happens at the peak. Remember that the y velocity of the peak is 0, so that means that velocity and acceleration are perpendicular in that case. Okay, moving on to our next question, we have a situation where an arrow is aimed directly at a monkey hanging from a tree. Okay, it's a soft arrow, it's like a dart, it's not going to hurt the monkey, don't worry. The arrow is fired horizontally, and at the instant that the arrow is released, the monkey lets go and begins to fall. Will the arrow fly above the monkey, below the monkey, or hit the monkey? So I'm going to think about my initial situation. We have an arrow moving horizontally, which means that initially there is no y velocity acting on the object. It only has that horizontal velocity. And we have a monkey that is hanging from a tree and releases the tree, so initially the monkey is also at rest. So in the y direction, both of these objects, okay, have the same initial y velocity. Both of these objects have the same y acceleration. So what's going to happen is, as the arrow flies through the air and the monkey falls, okay, at any given location, the arrow and the monkey will be at the same vertical height, because in the y direction their motions are identical. They're starting at the same height, they have the same initial velocity, and they have the same acceleration. So the arrow is going to hit the monkey directly. So I would just say, to explain this, that the objects have the same vertical motion. Okay, there's nothing different about their vertical motion, so they'll always be at the same height. So that means that the arrow will hit the monkey. Moving on to the last one here, we have two balls that are thrown horizontally from the same height. The one ball is thrown with 3 times as much velocity, though. So here's my first ball thrown with velocity of v. Here's the second one thrown with a velocity of 3v, both from a height of h. And we want to know which one's going to be in the air longer before it hits the ground. This one's similar to the monkey problem in that in both cases, the y velocity of the object when it's launched is 0. They both start at rest vertically. They both start from the same height. They both have that same acceleration going down of 9.8 meters per second squared. So once again, their y motions are identical, so they will take the same amount of time to hit the ground. Both of these problems really get at a bigger concept, and that is that x and y are independent of each other. So with the monkey, okay, the arrow had horizontal velocity, the monkey did not, but that doesn't change their vertical motion. Their vertical motions are the same. And same thing with the two balls being thrown. Even though they had different horizontal velocities, their vertical velocities initially were both 0, and so they still take the same amount of time to fall, because that horizontal does not affect the vertical. Moving on to this next one, we have a cannonball fired from a cliff at an angle of 27 degrees below the horizontal. And we're going to go ahead and think about how long it's in the air and solve for a few other things in this case. So here I have my projectile being launched at 27 degrees below the horizontal at a speed of 40 meters per second from a height of 25 meters. So first thing I'm going to do is I'm going to break that velocity into x and y components. So this x component is going to be 40 cosine of 27, and this y component is going to be 40 sine of 27. Now I'm going to go ahead and set up my chart in the x and the y direction. I know always that my acceleration in the x is 0, and my acceleration in the y is negative 9.8. I just found my initial velocities in the x and y, so the x is going to be 40 cosine 27, or 35.6 meters per second, and that y comes out to be 18.2 meters per second, so I can fill those two in. I also know that I'm launching from a height of 25 meters, so that means that my y displacement is going to be negative 25 meters. Notice I'm being very careful with my signs here in the y direction. I'm losing a height of 25, so that delta y is negative. I'm launching it down at an angle, so my initial y velocity is negative. And of course, my acceleration is going down, so that's also negative. I'm going to start with this y side because I have more information there, and I'm going to solve for some things using that. So I can go ahead and use my VFY squared equation first to find my final y velocity. I could solve for the time directly, but that would involve using the quadratic, so I'm going to avoid doing that, although that's perfectly acceptable if you would prefer to use the quadratic. But I go ahead and I solve for that final y velocity, and I get that it's going to be 28.6 meters per second. Since I had to take the square root, though, of that VFY squared, I need to do my sign check. And because my velocity is going to be going down when I land, that y velocity needs to have a negative sign in front of it. Now that I have my final y velocity, I can say negative 28.6 equals negative 18.2 minus 9.8 t, and I can solve for the time that this object is in the air, and that is going to come out to 1.07 seconds. So that answers the first question. I now can use that time in my x side to figure out how far the cannonball travels horizontally. I actually also know the final x velocity, but that doesn't really help us because we needed either our time or our displacement. I'm now going to go over the x side and use that time and my x velocity to figure out how far it went. So I'm going to use one of my delta x equations. That second term ends up going away because our x acceleration is just 0. That's why we have to use one of the delta x equations. So I end up getting that displacement is going to be my x velocity, 35.6, multiplied by my time, 1.07, and so I get an x displacement here of 38 meters. Which answers my second question. For that final question, what is the magnitude and direction of its final velocity when it lands? I'm going to go ahead and think about the x and y components of my final velocity when I land and put them back together. So I know that when this object lands, it's still traveling at a speed of 35.6 meters per second in the x direction, and I solve for that final y velocity, which ends up being 28.6 meters per second going down. So that means that my overall velocity will be this hypotenuse here, and I can solve for that angle as well. So I can go ahead and do the Pythagorean theorem here, 35.6 squared plus 28.6 squared equals c squared, and get that hypotenuse, which is the magnitude, ends up being 45.7 meters per second. In order to get the angle, I'm going to use the tangent, and so I know the tangent's opposite, or 28.6, over the adjacent 35.6, and I end up getting that my angle, when I take the inverse tangent of both sides, is 38.8 degrees. So to wrap up this answer, I would say the final velocity, magnitude, and direction is going to be 45.7 meters per second, and I would just say 38.8 degrees below the horizontal. You could say south of east, that's how we've done it in the past, but typically with projectiles we just stick with above the horizontal or below the horizontal. Okay, so moving on to this problem, we have two rocks that are thrown from two different cliffs, one with a height of h and another with a height of 2h, and we want to solve for some things about these two rocks. So we're going to start here with this one that's thrown from a height of h. We want to derive an expression for the time it's in the air and the distance traveled. Okay, so we're going to set up our charts here in both the x and y direction. So in the x, we know it's launched with a velocity of v. That will also be the final because the acceleration is 0. We, of course, always know that. In the y direction, it's thrown horizontally, so our initial velocity is 0. It's thrown from a height of h. That means our y displacement is negative h, and our y acceleration is going to be negative g. I'm going to start with the y side here because I have more information there, and that's going to allow me to solve for my time. So I'm actually going to use my delta y equation. It doesn't end up being a quadratic here because that first term just goes away since our initial y velocity is 0. So I have negative h equals 1/2 times negative g times t squared. I'm going to move the negative g over and multiply both sides by 2. And so I end up getting 2h over g equals t squared, which means that my time that's in the air is going to be the square root of 2h over g. So that answers my first question there, the time that's in the air. For the distance traveled, I'm going to have to use my x side. Using that delta x equation, that second term goes away, and so I have that my displacement horizontally is just going to be my initial x velocity, v, multiplied by my time, which is the square root of 2h over g. Okay, and so I get an expression here for my horizontal velocity, which is just v times the square root of 2h over g. Unfortunately, we can't simplify it any further than that. But I do have it in terms of hv and fundamental constants, so that works as an answer to the second question. For the third question, I'm going to think about what changes. I have my original setup, so what changes when I'm thinking about the rock thrown from the higher cliff. The only thing that really changes is my delta y. My initial y velocity is still 0. My acceleration of the y is still negative g. So I'm going to go ahead and use this equation here and resolve for the time that second rock is going to be in the air. Once again, that first term goes away, and so I have negative 2h is equal to 1/2 times negative g times t squared. Again, multiply both sides by 2 and move that g over, and I have 4h over g equals t squared. Take the square root of both sides, and so my time is going to be the square root of 4h over g. Determining that horizontal distance, I'm going to use this equation, and the only thing that's going to change is that t term. My initial velocity is still v, so I get that delta x now for this higher rock is going to be v times the square root of 4h over g. And I'm going to call that delta x prime because that's my new delta x. Okay, this is one of those new old situations. So what I'm going to do to combine these is solve both of these for v. So I'm going to say delta x prime over the square root of 4h over g equals my velocity, and delta x over the square root of 2h over g equals my velocity as well. And we can set those two equations equal to each other. So here's where I end up getting, and I know this is a little bit messy with all the square roots and stuff, but I actually see that both sides have that h over g term within the radical. So I actually can divide that out. What I'm basically doing is multiplying both sides by root h over g. And so what I'm left with is delta x prime over the square root of 4, which is just 2, equals delta x over the square root of 2. I can multiply both sides by 2 here, and I find that delta x prime is equal to 2 over root 2 times delta x. So that's how much further it goes. This does simplify, though, to delta x prime is just equal to root 2 times delta x. So that number there, that's the factor of how much further it goes, and either one would be acceptable as an answer. So one last one here with a long jumper running and jumping at some angle theta. They fly up in the air and they land down on the ground some distance away. Tells us it's a horizontal distance of x. Okay, and we want to know what the initial velocity was of the long jumper. So although I don't know that initial velocity, I can still think about my components here in both the x and y direction. Whatever that initial velocity is, the y component is going to be v sine of theta, and the x component is going to be v cosine of theta. And I can fill in the other things I know about this situation. So I always know here that my x acceleration is 0, my y is negative g. There's a few other concepts that I know, so I could use information about the peak where vy is 0 and my time is half the total because this is a symmetrical situation. Or I could use stuff about the end where my delta y is 0 and my vy is just the negative of my initial. Since I'm given x, the horizontal distance traveled by the object overall, I'm going to be thinking about this stuff that I know at the end. And that means that I'm thinking about the entire time that the object is in the air. So I'm going to say my delta y is 0. My final on the y is negative v sine of theta. I'm also going to put in x for my horizontal displacement, and I can say that my final x is v cosine theta, although that doesn't really help us too much. So I ultimately want that horizontal distance traveled, and so I'm going to first think about my x information and set up an equation using that. So in the x, using my delta x equation, that second term goes away, and I get that my x displacement, which is just x, is equal to v cosine of theta multiplied by t. So this is almost okay in terms of solving this. I know x, I know theta. The only problem here is this t. We need to do something about that. So I'm going to use my y information to go ahead and solve for t in terms of some other things. So in the y direction, almost any equation will work, really, anyone that has t in it. But I'm going to use my VFY equation, and I'm going to say negative v sine of theta equals v sine of theta minus gt. I'm going to subtract that v sine of theta from both sides, so I get negative 2v sine of theta equals negative gt. And solving for t by dividing both sides by negative g, I get 2v sine of theta over g is equal to my time. I can now take that and substitute that in back into my x equation, and so I get that x is equal to v cosine of theta times v 2v sine of theta all over g. I'm going to do a number of things here. I'm going to combine those two v's. I'm going to multiply both sides by g. And what I end up getting is x times g equals 2v squared times cosine of theta times sine of theta. Solving for v, I'm going to divide both sides by 2 cosine theta sine of theta, and that's going to be equal to v squared, and I take the square root of that, and I get that v is just going to be equal to the square root of xg over 2 cosine theta sine theta. So there's my answer. There is a nice little trig identity with this term down here, and you could use it, and that's the 2 cosine theta sine theta is actually equal to sine of 2 theta. So you could say that v is the square root of xg over sine of 2 theta. But we certainly don't need to go ahead and make that substitution. It would just be, if you happen to remember that trig identity, you could use it. All right, we have one last little concept to talk about here before we wrap up projectile motion, and that is what angle achieves the maximum range when launching something horizontally. So the key is when you're launching something, if you want it to go as far as possible, the greatest horizontal distance, that's what range means. You want to increase the time in air, which results from having a lot of y velocity, and you want to increase how fast it's moving horizontally, which results from having a lot of x velocity. The problem is, if you launch it straight up in the air, you have a ton of y velocity, but no x. If you launch it horizontally, you have a ton of x, but no y. So what do? We split the difference. And at 45 degrees, we end up achieving the greatest horizontal distance if it's a symmetrical launch. Okay? So that's one important concept to keep in mind. Something else to keep in mind here is we have a bunch of these launches, and many of them are complementary angles, meaning they add up to 90. And what I want you to notice is those complementary angles, like 15 and 75, land at the same spot, as do 60 and 30. This is going to be true for any complementary angles. Although the higher angle might travel further up in the air, it will land at the same spot as its complementary angle, because that complementary angle, although not in the air for as long, is traveling faster horizontally. Okay, so that's something else to keep in mind. Again, two kind of random concepts, but I think they're worth mentioning.